All right. Good evening, everyone. My name is Vikrant, and some of you might know me from the previous sessions. It gives me great pleasure today to introduce Ms. Shreejaya, who happens to be a very good friend of mine, a classmate at St. Joseph's College, and also a teaching and research intern at Nakshatra Sciences. Without further ado, Shreejaya, you can proceed with your session today.
Yeah. Hello, everyone. I'm Shreejaya. I'm doing MSc Physics at St. Joseph's College. So today I'm going to, I hope I'm clearly audible.
Yes, Shreejaya, you can continue.
Okay. So today I'm going to take a short session on basics of polarization. It won't take I think it won't take more than 30 minutes because there are obviously advanced topics which will help you in your project, so I'm going to cover them in the next sessions. So that might be in a weekend or something. Let's see about that. So today I'm going to cover the topics: introduction of polarization, types of polarization, how is polarization achieved. There are a few types, so I'll explain that. Malus Law, Poincare sphere, and the rest of them I'll cover in the next session. So basically, what is polarization? Polarization helps us restrict the electric field components in one plane. As you know, natural light is unpolarized and it has electric field components in all directions. So basically, polarization is an operation on the
Shreejaya?
light. Yeah.
Yeah, can you put this on full screen?
Yeah.
And I see there's a chat that says that by Naren saying you're not audible. Naren, can you check your audio once again if you've connected properly? And yeah.
So
All right. Sorry for the
full screen
interruption.
is
You
fine
can,
now? Full screen
yeah,
is fine?
audio is fine and screen's fine. You can continue.
Okay. Yeah. So polarization is required in order to restrict this electric field components to one plane. So if we have two components, then we restrict them to two different planes perpendicular to each other. So this is a symbolic representation. You might have studied in your uh, undergrad or UC or something. So this is the notation for unpolarized light. This is for the vertical linearly polarized light. This is the vertical plane linearly polarized light. This is the horizontal one. C is for the horizontal one, and the last one is again unpolarized light. Yeah. So the types of polarization, there are three types: linear, circular, and elliptical. So by linear, what I mean is we have two planes which have two, each one of which have each one have electric field component. They are linear to each other and their phase difference is either 0 or 180 degree. So what the pattern we get is a straight line, and if this was this, so this is the propagation axis. So the plane is vertical in the propagation axis. If the the component is vertical, if the component was horizontal like this, we would get a line parallel to or coinciding x-axis. This is the linear polarization. Next, we have circular polarization. In this, we have two components which are perpendicular to each other, two electric field components in two different planes which are perpendicular to each other, which have the phase difference 90 degree. You can see here they have the 90 degree, and they give the pattern of a circle, hence it is called a circular polarization. And next we have elliptical polarization. We have two planes which are perpendicular to each other, and in this case the amplitude of the two electric field components are different, whereas in the circular polarization the amplitude of the two electric field components are equal. And in the elliptical polarization, the two planes are perpendicular to each other, and their phase difference won't be equal to 90 degrees. It will be either greater than 90 degree or less than 90 degree, and hence we get this elliptical pattern. So we'll see that linear and circular polarization are special cases of elliptical polarization by this mathematical derivation. I've just put a few steps. You can go through it, or like some of you might already know this, so you can revise. So when we consider two electric field components in two planes, Ex and Ey, Ex is in the is along the x-axis, Ey is along the y-axis. You can see from the I hat and j hat, and E naught x is the amplitude of Ex, and E naught y is the amplitude of Ey, and they both are propagating in the z-axis. You can see here from the propagation vector, and epsilon is the phase difference between the two components. Now you can rearrange this and obtain these equations. Then using the relation cos a plus b for this cos kz minus omega t plus epsilon, you can expand the second equation and write it like this. Using the relation cos square x plus sin square x is equal to 1, you can replace sine kz minus omega t here with this one, because you have, as in using the relation, you since you have cos kz minus omega t here, you can replace it and write like this, and you obtain this equation by fully squaring and simplifying further. You obtain the second equation, which is the form of ellipse equation. So ellipse, when it has a tilt, or when it makes an angle with respect to x-axis, will give something like the second equation, or the general expression that I've written here, and the angle is given by this. This is just the diagram that I've written for, so you can see the tilt that this ellipse is making with the x-axis. These are all the amplitudes. So the angle of tilt for our case will be obtained like this. So using this, we can obtain three cases of polarization. First one will be when there is no tilt, or when the phase difference is plus or minus pi by 2 or plus or minus 3 pi by 2, etc. Then we obtain this. Then we obtain the general form of ellipse equation. And when the amplitude of the two electric field components is E naught, then we obtain the equation of circle, which is a circular polarization. This is elliptical polarization, and this is circular polarization. So this phase difference, when it is even multiples of 0 or odd multiples of 0, which also includes even multiples of pi, odd multiples of pi, which also includes 0, we obtain two straight line equations given by equation 5 and 6, which have the slope plus or minus ratio of the amplitudes of the electric field components, and this corresponds to the linear polarization. So the linear polarization and circular polarization are just the special cases of elliptical polarization. Next, we'll see the two kinds of linear polarization that we already discussed once, but yeah. So this is the axis of propagation, and we have the plane, like the electric field component vertical with respect to the axis of propagation. Then we obtain vertical linear polarization, and when the uh, the electric field component is horizontal along the wave of the propagation axis, we get the horizontal linear polarization. Next is the types of circular polarization. You can see two planes here. One is in blue, the other one in green. So when the so you can see the blue electric field component and then the green one. You can see that if you extend it this way, the phase difference between the blue and the green is minus 90 degree or minus pi by 2. So the pi by 2, and the red line that will show how the wave will propagate, and that is you can see a circle here, that is a circular polarization which is right handed. So when the phase difference is minus 90 degree, it will be right handed circular polarization, and this is vice versa. You can see that the phase difference is plus 90 degree, then it will be left handed circular polarization. And this right handed and left handed, it is from the point of view of the observer. If you stand behind the screen and observe the wave from the point of view of the source that is behind this, then right handed for us will be the left handed circular polarization to you if you check from the other side, and similarly this. So it's all dependent on the point of view, but conventionally it is always from the point of view of the observer, which is this notation: right circular and left circular. Transmission axis. So basically, if this is a polarizer, then transmission axis is defined as the axis of the polarizer or analyzer, such that the electric field component parallel to this axis will only be transmitted and rest all is discarded or absorbed. So this is the unpolarized light. It is going towards the polarizer, and if this is the transmission axis, then only the electric field component vertical to the through the propagation axis will be transmitted. And similarly, if the transmission axis was parallel the opposite direction, the horizontal direction, then only the uh, electric field component which is horizontal to the axis of propagation will be transmitted to the other side. So methods of achieving polarization. I have included three types in this: polarization by reflection, polarization by selective absorption, and birefringence. So polarization by reflection is a commonly used method where you incident a light, for unpolarized light, on dielectric medium at some angle called the Brewster angle given by this expression, and whatever you obtain on the other side is as in the reflected wave is plane polarized. Plane polarized is another name for linearly polarized, and this notation, as I showed in the beginning, this is for the horizontal linear polarized light. So yeah, this is the horizontally linear polarized light, and the Brewster angle is given by this expression, that is tan of Brewster angle is the ratio of the refractive indices of this second medium to the first medium. Birefringence. So birefringence is the property of certain materials which have two refractive indices, and this will affect the way light will react to this. So basically, the light will split into two components, and these components will travel at different velocities. And this, which one travels faster and which one travels slower, depends on the type of the crystal we are considering. So the two components are called O ray and E ray, ordinary ray, this one, and extraordinary ray. So ordinary ray will, both of them are plane polarized light or linearly polarized light. Well, ordinary ray is vertically polarized light, and extraordinary ray that we obtain is horizontally polarized light. The next one is polarization by selective absorption. So using something called wire grid polarizer here and here, we can obtain polarization. So as you can see, we have parallel wires here. So when unpolarized light falls on it, only the component which is perpendicular to these wires is passed, and we can see it on the screen, or we can detect it basically. This is vertical. So the transmission axis of this will be uh, vertical, even though the wire grids are parallel. So the transmission axis is vertical. That's why only the vertical component is getting transmitted. Similarly, we have a wire grid here, which has vertical wires which are parallel to one another, and the unpolarized light will pass through it, and rest of the will pass through it only the horizontal component with respect to the propagation axis is transmitted, and the rest of them are absorbed. So you may, like, we need to know what is the intensity that we obtain here. No, not just here actually. We need to know how much, if there are two polarizers, not just the wire grid polarizers. If we have two polarizers, then what will be the intensity that we get at the end? So we have something called the Malus law. In this case, the unpolarized light is incident on the polarizer. It gets polarized, and this polarizer will go into an analyzer whose transmission, this red line, the axis, it represents the transmission axis. So this analyzer transmission axis is makes an angle theta with respect to polarizer's transmission axis. So the intensity of the light that is transmitted from the analyzer, that the detector detects, is given by this expression, number 8. I is equal to I naught cos square theta. I naught is the intensity that the polarized light has. So this is an important expression. Next we have is Poincaré sphere. This is Poincaré sphere. I'll come to that. So this is just the like I showed before. I showed where is it? Yeah, this diagram. It is the polarization ellipse. So this is again the same, but it has a little few more details into it, and I have changed the notations of some angles. So this tilt we have already talked about it. It is tau, and then it's the angle that ellipse makes with the x-axis. Then what we have is handedness, the gamma. So gamma is given by arctan Ey by Ex, the two components, and then ellipticity, this blue color angle, it is arctan, that is tan inverse of y by x, that is minor axis by, yeah, minor axis by major axis. Okay, these become important for the next session. That's why I'm just mentioning it here. When I take next section, I'll explain more about it. And this is the sphere. This is just a Poincaré sphere is a graphical tool in order to understand the different types of polarization, like polarized light that I already explained. So we have two great circle, as you can see. This one, it is equator. The other one, which has north pole and south pole. So north pole, at the north pole, we have left circular polarization represented by the circle, and at the south pole we have right circular polarization. I already told negative 90 degree, positive 90 degree. And then the intersection between the equator and the x-axis. If you consider this as x-axis and this as y-axis, then the intersection will give you linear polarization. The straight lines, one at 45 degree, the other one 135 degree, and the intersection between the equator and the other great circle, this one will give you horizontal linear polarization here and vertical linear polarization. It is just a representation of the different types of polarization. It's for visualization. And then these points are actually represented by certain vectors, and these vectors can be explained from certain parameters called the Stokes parameters, which I'll be discussing in the next class, next session. So that's it for now. This and all I'll cover in the next class.
Awesome. I think that concludes your session. If there's any questions, please go ahead. Okay, I see there's no questions. Yep. Oh, that's nice. All right, in that case, I think we can conclude.
Okay.
Let me just check once again if someone has any question, and I don't see any raised hands either. So, all right, cool then. I think this is a good place to stop, and I'm hoping that all of you will be present for the next session on advanced polarization. I'd like to thank Shreejaya for taking out the time with us, and thank you all for joining in. This was a very short introduction, so I hope you've picked up on the basics, and all the best for your projects. Thank you.
Thank you, everyone.